Hello everybody! Welcome to the overview of the climate data and bias adjustment behind the Pan-European Climate Database, PECD in short, version 4.2. The topics that will be covered are a list of past and future climate indicators, their temporal and spatial characteristics, and some examples of applications to the PECD-related analysis. Moreover, we will explore the general concepts behind the bias adjustment methods of the delta and the CDFT and their application to the PECD climate indicators. The climate indicators that will be part of the PECD 4.2 database are temperature, population-weighted temperature, precipitation, wind speed at 10 and 100 meters height, and global horizontal irradiance. All of them will be delivered in a gridded format, the net CDF format, at 0.25 degrees resolution, that at the European latitudes correspond roughly to 25 km spatial resolution. The same indicators will be also available at onshore and offshore zones and for temperature also in selected cities. Past climate indicators will be based on the ERA-5 analysis from ECMWF, covering the years from 1950 to August 2024 at hourly resolution. Future climate indicators are based on 6 models from the CMIP6 project, which name is reported in the list on the right. 2 shared socioeconomic pathways will be considered, the one 2.6 and the 2 4.5. The climate projection models cover the years between 2015 and the end of the century at hourly resolution. Regarding now the application of climate indicators in the PECD domain, the figures represent in the top left an example of variability of the 6 climate models for temperature given a specific SSP, while in the bottom, for the 10-meter wind speed, the variability of the SSPs for a fixed climate projection model. In the top right, a comparison of the temperature distribution for 3 climate model and historical climate, while at the bottom we find an example of a map of gridded wind speed at 100 meters for a particular timestamp and climate projection model. As can be seen from these pictures, the spatial and temporal characteristics of the climate indicators, combined with the capability to utilize an ensemble of models and scenarios, enable a comprehensive and optimal assessment of climate patterns across past, present, and future timelines. This approach enhances the accuracy of climate projections and improves our understanding of the climate, allowing for more informed decision-making in response to climate variability and change. Now, moving to the topic of the bias adjustment, the delta method allows the adjustment of a source dataset based on a target variable by calculating the change factors or deltas from the average datasets, as explained in the top picture. In particular, the averages of the adjusted source and target datasets are matched by performing a scaling adjustment of the source with the delta factors, as shown in the bottom picture. From the bottom picture distributions, it can be noticed that the mean of the corrected source, that constitutes the output of the bias adjustment procedure, matches exactly the average of the target distribution. The delta method is the simplest bias adjustment method, although it is limited by the assumption that the bias is constant in time. The cumulative distribution function transform method, in short CDFT, is a probabilistic downscaling method that models the statistical relationship between a target dataset and the source by a projection model. These non-parametric correspondences, or transfer functions, are applied to a predictant CDF to obtain the corrected output. In particular, the method uses the CDFs of target and source in a common historical period to model the future period CDFs, assuming that the future predictant CDF is known, as shown in the picture. In particular, in the picture, the transform between source and target is represented in black, while the red lines represent the application of this transfer function to the predictant to obtain the adjusted output. This method is more accurate compared to the delta method because it can capture nonlinear behaviors and climate change signals or trend, but it is limited by the computational complexity and the large computational times required. Regarding the application of bias adjustment in the PECD database, in version 4.2, the ERA5 wind speed at 10 meters and also at 100 meters are corrected with the delta method, using the global wind atlas version 2, differently to what is done for PECD 4.1. The projection variables are adjusted with the CDFT method, more suited for climate projections, as seen in the previous slide, except the global horizontal irradiance, where the climate trend is negligible, corrected instead with the delta method. For all these methods, the corresponding ERA5 variable has been used as reference. Looking now in more detail to the application of the delta method in the adjustment of ERA5 wind speed at 10 and 100 meters, the first formula indicates how the delta factors have been computed by taking the ratio of the global wind atlas and the ERA5 10-year average. Then, the wind speed at 10 and 100 meters at each time step have been corrected using the second equation. In the climate projections, the delta method has been used to adjust the global horizontal irradiance. First of all, the averages of the source and target dataset have been calculated and are displayed in the top and middle map. Then, for each grid point, the predictor time series has been corrected using the delta factors. The original predictor and the corrected output PDFs are displayed in the bottom panel. The effect of the displacement of the mean of the distribution of the predictor due to the correction is clearly visible. In the PECD database, the CDFT method has been applied for the adjustment of temperature, wind speed and precipitation of the climate projection models. The adjustment is performed separately for each month and hour to account for the seasonality and the diurnal cycle variability. The moving window approach, which the schema is reported on the right, addresses non-stationarity in climate projections, where the assumption that model and reference distributions retain the same shape is not valid. This is particularly relevant for variables such as temperature, given the non-negligible trends as shown in the left figures. The left figures report the CDFs of source, target, predictant and output for two different correction windows, where the temperature extremes values are very different due to the climate change trend. However, this difference is preserved by the adjustment thanks to the characteristics of the CDFT method. Thanks for the attention. For any question, please don't hesitate to contact us.